Hello, in this video I want to show you how I would draw the mechanism of a radical halogenation of an alkane. It's important that it's important that I say alkane because this is the only reaction that I teach my students where the starting material is an alkane. And that will be important when we do multi-step synthesis problems. The idea here is for me to draw what I expect as the answer, and then I'll go back and annotate some of the more interesting points about this mechanism. Excuse the noise. Today's Sunday, so it's a big chore day. That's the dishwasher running right now. Okay. For the mechanism of radical halogenation, we do label the steps, and we do use fishhook arrows. Initiation occurs with homolytic cleavage of the BR, one fishhook to the left, one fishhook to the right. I don't normally use equilibrium arrows for radical mechanisms. And I typically draw both bromines, but you don't have to. Seeing that, I just want to mention that when my students draw the products of a reaction, we don't worry about any minor products or products that don't contain carbon. Normally I would say draw the carbon-containing product or the main carbon-containing product. And so I'm not telling you where this other BR is, okay? I'm just showing you the main product. Okay, that's initiation. The next is propagation or propagation. There are two steps for propagation. Again, I will go back and I will annotate in writing some of the more important points, but right now I'm just showing you how I would draw the mechanism. You take one of the sigma electrons and you put it on the carbon, tertiary carbon. You take the other sigma electron and you meet in space the electron from the bromine to make a bond, HBr. What we get is a alkyl radical plus HBr. Now, I mentioned before when I asked for the products, I'm not worried about the other non-carbon containing products, but I like to draw in a mechanism all the products at each individual step. The second reaction of the propagation is you take the same radical alkane that we just made and we react it with not Br radical, but we react it with Br2. And we're going to do the meet in space again. One electron there, one electron there, one electron there. We do get our product. And that's how we would prefer to get the product. There are going to be other ways, which we'll see in a couple seconds. What's interesting here is that this Br radical that was generated in the second step of propagation can go back to the first step and start the process over again. The next couple of steps are called termination. And that's the combination of two radicals. For instance, Br radical plus another Br radical. You don't have to draw the lone pairs of a radical. You're allowed to leave them off. And we get this, Br2. In that case, what we could do is we could repulse the Br2 to homolytically cleave it. I should have wrote actually heat or light. Okay, that is the abbreviation for light. There's another termination step that could happen. If it's really the combination of two radicals, Then let's look at all the different combinations of two radicals. The next combination I want to see is this, and we get the product again. This is the other way that we could get the product. The product from the propagation, though, is preferred. I'll explain that later. The other two radicals that can bump into each other, and this is the one that's not very productive, are the two alkyl radicals. Again, if we make this in a termination step, we could always shine light on it again, start the process over. If we make this, that's fine, that's the product. But if we make a lot of the product of the third termination step, essentially your reaction is dead, terminated. So we have that alkyl on the left. We make a bond to the alkyl on the right, and we have the same carbons. You could always double check. We have 7 carbons here, plus another 7. This should be 14. We make a bond between these two carbons. Okay, that is what I would expect for the mechanism. I don't normally write or note the rate determining step. Once this happens, then the reaction is it goes along pretty quickly. Some notes. Let me write these notes in a different color. Let's try orange. Okay, the first thing is there's one initiation step. There are 2 propagation steps, and there are 3 termination steps. Let's see, what else can we say? In the 2 propagation steps, gotta remember, if you take a look, it's a non-radical plus a radical. But in the termination steps, it's 2 radicals coming together. You see the difference? Okay. The next thing is, I'll put here lone pairs are optional. You don't have to draw them. Like this bromine would have 3 lone pairs and 1 unpaired electron. This one's important. The first propagation step, we are abstracting. You'll hear that word, maybe. That's removing a hydrogen. Abstracting and literally, it is a hydrogen. It's not a proton. It's not a hydride. It's the hydrogen nucleus with one of its electrons. So this is, in fact, removing a hydrogen. In the acid-base module, I made it very clear we're not transferring hydrogen. We are transferring just protons. But here, it's a hydrogen. Okay, now the kind of a tricky part. We want to avoid termination because literally it terminates. If we run out of radicals because of any of these terminations, we cannot do propagation. So while this is okay, it's not great because it's dead. The reaction stops. I would rather make the product this way so we could take our Br radical, this one right here, and recycle it back there. Let me finish my thought at the bottom. Want to avoid termination steps. So the idea is to keep the radical concentration low. I'm writing fast because I think this is a very interesting point. We want to keep the radical concentration low to lower the probability of 2 radicals hitting each other, to decrease probability of two radicals finding each other. That will actually promote the two propagation steps, and it will keep going and going and going. So that will actually promote, like encourage the propagation steps. Okay, let me zoom out a little bit. I think that's pretty good for a one-page study sheet for the mechanism of radical halogenation of an alkane. I just thought of another thing. Your radicals, so many good points here. Your alkyl radical is flat around the unpaired electron. So the alkyl radical, sp2 carbon, this one right here, okay, and therefore it is flat. And I didn't show it here, but when that bromine comes in the second propagation step, it can come in from the front wedge or back dash, meaning that you will get a racemic mixture if you form a chiral carbon. So here will be racemic mixture. Okay, now I'm done with the annotation, I think. Be able to reproduce the mechanism, the stuff you see in blue and green. Try to understand sort of these interesting annotations, the ones in orange and pink.